Okay, so our graph, before we labeled it, could have represented any function y equals ax to the 1.6. Now that we've labeled it in green with these coordinates and made an estimate to kind of check ourselves, okay, we know that when x equals 2, a has to equal 10. Y has to equal 10. So we're going to replace y by 10, and we're going to replace x by 2. So now we're going to be able to calculate our value of a. Our value of a is going to be what? It's going to be 10 divided by 2 raised to the 1.6. Now we can go to our calculator and calculate 10 over 2 to the 1.6. We get approximately 3.3. So now our function y equals ax to the 1.6 becomes the specific function y equals 3.3x to the 1.6. So we've got a class of functions here where any value of a gives us a different function in that class, but now we've got the specific function, or at least an approximation to the specific function that fits the situation, that fits the given information. Now let's see what happens if x equals 6. Because we've estimated that if x equals 6, y should equal about 70. Now I suspect that might be a bit of an overestimate since my gap between 4 and 6 is greater than my gap between 0 and 2 or between 2 and 4, but still let's just test my not very precise estimate. Okay, if x equals 6, well then y is equal to 3.3. I didn't leave myself much room to write that in, but that's 3.3 right there, multiplied by 6 raised to the 1.6 power. Now you have to raise 6 to the 1.6 power and multiply by 3.3, and you're going to want to use a calculator for that, and there's no shame or problem with doing that. Let's see what we get. Okay, now I didn't attempt to raise 6 to the 1.6 in my head. Wouldn't have been very precise. What we get rounds off very close to 58. Okay, so 70 wasn't a terrible estimate. 58 would have been better. And if I had my 6 over here, might have been a lot closer to 58 with my estimate, but it looks like I still had an overestimate. Still, the point of doing this estimate and doing a confirmation is that it makes sense that the model should be this. This is close enough to our estimate to confirm what we hope to be true, that y equals 3.3x to the 1.6 is a pretty good model for a graph where y values triple when x values double, and then the specific result that if x equals 2 gives you y equals 10, then the specific function is y equals 3.3 times x to the 1.6. Now we could relabel the same graph for a different situation. What if y is 160 when x equals 30? Well, then I can't pick my very favorite point in the graph. I'm going to have to pick my second favorite point. And my second favorite point is over here. And I'm going to label this in a different color. Okay, x is 30. I could have picked any point on the graph, and I picked that one. So x is 30, and y is 160. So now I can, do some labeling here. It's going to be a little difficult to do that because these labels are pretty dense. These aren't too bad. If this is 30, then 1/3 of that distance is probably here, here, here. I'm going to say that would put 10 here and 20 about here, 30 about here on the x-axis. On the y-axis, 160. Well, I could cut that in half. That put us about here. So this would be about 80. And half of that would be 40. That would be maybe along about here. That's a little high, maybe a little lower than that, but somewhere along in here. Okay, so we have a labeling, and of course the labeling could be done with a lot more precision. Doesn't have to be done by eyeball. But now I have a good relabeling of the graph. The characteristic y is 160 when x is 30. Now if I plug my x and y values into this general form, y equals ax to the 1.6, this time I'm going to get a equals 0.69. You can verify that for yourself. So that the model where y is 160 and when x equals 30 is y is approximately 0.69x to the 1.6. And to check that, we could estimate the value of y when x equals 20. That looks like that's going to be just a little over 80, maybe as much as 90, but somewhere between 80 and 90. And as it turns out, if we plug 20 in for x, we get something like 83. So that's very consistent with our graph, much more consistent than our last estimate, although our last estimate wasn't that bad. And if I make an estimate for x equals 10, now that's going to put us somewhere over here. If this is 40, then this is probably around 20. So let's just see how that works out. That didn't work out great, but it's okay. I estimated 20. It was actually more like 27, a little closer to 30 than it was to 20. But that kind of confirms that the graph is reasonably modeled by this function. It kind of confirms our model and also, again, reinforces what's going on here. Now let me comment that you defeat the entire purpose of the exercise, which is to move you a little bit further along this level of abstraction to the idea of a function family, that there are certain curves that have a shape that fits certain phenomena. You do this geometrically. You do this by some sort of construction, whether it's some of these you can do with a compass and a straight edge, but some sort of a construction where you're cutting x values in half or doubling x values just by visually rather than by measuring, although you could do it by measuring, and you're tripling y values and then you're matching them up. Okay? I prefer you do that visually by estimation, but of course you can always do that more precisely. Gives you a graph of a certain unique shape when you know the factor. Okay? We didn't do it, but almost everybody constructs their graphs by making a table like this. And that's really what we want to get away from. We want to think of these functions as abstract entities, not something we get by plugging numbers in and then labeling this 1, 2, 4, 8, and so forth. Labeling this 1, 3, 9, 27, and so forth. We don't want those numbers. We don't want those numbers on our graph because they clutter things up. They get in the way when we're trying to deal with real information. Okay, so we don't want that. And we don't want this. So we're going to put a big X through this. Don't feel too badly if you did this, because everybody I think did, but understand that that's not the way we did it, and that's not the process that we used. When we all got up at the board and constructed these graphs, we didn't have any numbers. We did an unlabeled graph that just showed a shape. Also, we spread the graph out. When you do this, you set your scale up, and you're going to get a big old skinny graph. You're going to tend to get a big old skinny graph, at least for a factor of 3. If you had a factor of 1/3, you'd probably get a really flat graph. Construct the graph, then adapt the constant A to the information you have. So now addressing problem 2, we want to do a graph for factor 8. Again, it's a good idea to start out here So our first x value is going to be down here. Okay, labeling the x-axis, not the point. Okay, so we cut that x value in half, puts us about here. Cut that in half, puts us about here. Cut that in half, puts us about here. Now we're reducing the y values by factor 8, so we're not going to be able to cut the x values in half too many times, or the y values get really close to 0. Now, factor 8, well, we could go down here and kind of make a little note. There's factor 2, and half of that would be a factor 4, and half of that would be a factor 8. So our second x value would be all the way down here. And our next one would be 8 times as close to the origin. So that would be all the way down here. And that's actually as far as we're going to be able to go and still have the marks be visible outside of the x-axis. So here we go. Here's our first point. Our second point is going to match this with this, of course moving back toward the origin. Our third point will match up here. And our fourth point is going to be down so low we're actually not going to be able to see where it diverges from the axis. So, and of course we know that 0, 0 should be a point on this graph. Again, keep having x, we approach 0 from this side. Keep reducing y by factor 8, we approach 0 from this side. We never really get there, but we use this as what we call a limit point. And so our graph is going to pretty much stay in the x-axis until it gets out maybe about here. We're going to go through here, and it's going to keep on getting steeper and steeper, and I missed that point, but you see what should have happened. So right there is a reasonable approximation to the graph. Okay, now we pick a point on the curve to be 1, 1. Okay, so again, I'm not going to pick one of these labeled points. That almost defeats the purpose. But let's just say that my favorite point on this graph, or the point that I deem most appropriate to whatever it is I'm trying to model, is here. So here would be x equals 1, and here would be y equals 1. Okay, because the instruction said pick a point and label it 1, 1. Okay, don't think I located that particularly well, but that's okay. Right, now we label the rest of the graph. Well, to label the graph, I'm going to cut 1 in half here, and I think right about here ought to be 0.5. And down here, okay, I'm going to come about halfway. Maybe that's right. That would be 0.5. Now I can cut that down more. If that's 0.5, then this is probably about 0.2 and 0.1 and 0.3 and 0.4, and then 0.6, 0.7, 0.8, 0.9, and I can do the same sort of thing down here. I'm thinking that 0.2 maybe ought to be about here. So 0.1, 0.3, 0.4, and then 0.7, 0.6, 0.7, 0.8, 0.9, 1. Okay, so now I've got a reasonable labeling of the graph. Let me make that 2 a little bit bigger, a little bit clearer. Okay, so right there is a reasonable relabeling of the graph.